Many of you are probably familiar with Todd and his work in the industry for a long time. He's been the recipient of the 2013 MASNA award, and today his talk is a Seawater Primer for beginners. So everybody give Todd a hand, welcome him to the stage. Thanks. Thank you.
Did it go? Oh, shoot. All right. There we go. All right. Well, thanks for coming. In a lot of ways, I'm probably the worst person in the world to give a chemistry talk because I don't really like chemistry. I've never been good at it. I'm not really big on testing my own water. And the tanks I keep are probably nothing like the tanks you hope to keep. I breed fish, which means that all of my tanks have either 2 fish and nothing else, or they have 1,000 fish. So the parameters I'm dealing with are going to be a lot different. But since I do teach courses like introductory biology and talk about water molecules and things like that, I guess I have a little bit of fundamental information I can share with you. So I'm Todd Gardner. You probably know me from some of the breeding work I've done over the last few years, or my Facebook photos of our family adventures, or my underwater shenanigans. I also want to throw in that if you have any real serious water chemistry questions, because you want to keep a really fancy tank like this one, my friend Randy's tank at Pratt Institute, don't ask me. Ask a water chemistry expert like Bob Stark or Craig Bingman, someone that knows a lot about advanced aquarium chemistry. I'm going to talk about some very basic stuff here today, starting with water, the substance and the molecule. We know it's special stuff. It makes life possible on our planet, not only because we need to drink it and we need it in our cells, but it makes the Earth a livable place in terms of its ability to stabilize temperature and other parameters on our planet. Water has a long history on our planet, which sounds kind of funny, but the oceans haven't always been here. For the first more than 500 million years of our history, there was no water at the surface of our planet. It was mixed in with the molten rock, eventually gassed out through volcanoes, and it took about 500 million years before the Earth was cool enough for it to rain back down and fill our oceans to the point where the Earth looked something like how it does today. A little bit about the water molecule, very quickly. It's a polar molecule, which is not unusual. It's unusual for such a small, simple molecule to be polar in nature like this. What do we mean by polar? Well, because of the way the electrons are arranged between the oxygen and hydrogen molecules, and oxygen being kind of an electron hog, the electrons spend more time up around the oxygen and leave the protons of the hydrogen partly exposed. So even though there's no net charge, there's an uneven distribution of electrons, and so charge around the molecule. Oops. And when they get together, those opposite charged ends of the water molecules form these little attractions between each other called hydrogen bonds that are responsible for most of the unique properties of water, some of which we'll talk about today. One of the really important ones to us as aquarium people is that polar nature of this very small molecule makes it really good at dissolving ionic compounds. And a lot of what we're dealing with in our seawater is ionic compounds, like everyone's favorite, sodium chloride. Water molecules orient themselves around the positive and negative ions that comprise these ionic compounds and separate them. So it makes it a really, really good solvent. We also, as I mentioned, or maybe I didn't, but I'm sure you know, that the Earth is covered mostly in water. More than 70% of the Earth's surface is covered in water. If we look at a breakdown of that water, though, we see that the vast majority of that is salt water. Only 2.5% of the water is fresh water, and only a very small sliver of that is liquid water near the surface, rivers and lakes and things. And if you think about this, you have, if you look at these numbers and figured out, you see that only 0.007 of 1% of the surface water on the planet makes up this habitable liquid water that makes up rivers and lakes and ponds and stuff. So the point is, most of the surface of the planet is covered not just in water, but in salt water, undrinkable water, water that our saltwater fish wouldn't want to live in. So a lot of the surface covered in water. One of the qualities of water, though, I'm going to mention now is its heat capacity. So water is really good at holding its temperature. It doesn't like to give up heat, doesn't like to take on heat, and this means it doesn't change temperature very well. With so much water having such a high heat capacity compared to other substances, the oceans, this massive volume of water, maintains a very stable temperature compared to other places on the planet. What does this mean for us? It means that the things we keep in our tanks don't tolerate variations in temperature. They're adapted to very stable conditions, and that's not only about temperature. Another quick one I'll mention, at the changes of state, which happen on our surface all the time, going from solid to liquid and liquid to gas, there's big heat exchanges that further stabilize the surface of the planet, making it livable, but also, even more importantly for us, as aquarium hobbyists, stabilize the temperature of the oceans, further stabilizing ocean temperatures. The reason I included the thing about the water vapor, that enormous heat exchange that it takes to get water to change state, what this means for us is that as water evaporates from the surface, it takes away a lot of heat energy. So you can, if you have a tank that is borderline too high in temperature, if you don't want to run a chiller and you have a tank in a warm place or a place that's subject to getting warm, you can shed a lot of heat from the tank with evaporative cooling. Just like you can cool your body by sweating, you can cool the top of your tank by not having a glass lid on it. Keeping the top open and a fan blowing across it is a really good way of lowering the temperature below what it might otherwise be. We see this on the surface of the ocean. There are places, even within the tropics, this is the day-night temperature difference of the surface of the Earth in different regions. Notice that all the places where it gets a lot hotter during the day versus at night are on land. Over the ocean, temperatures stay very stable, and in a few areas where there's strong winds blowing, the temperature on the surface of the ocean actually drops a little bit during the day because of wind that picks up and blows across the surface. Just more evidence of this evaporative cooling. So, enough about basic oceanography. I want to talk about some of the terms you're going to hear as far as water chemistry when you're dealing with your tanks. These next few terms, dissolved solids, salinity, and hardness, all have a lot of overlap. They're all referring to things that are dissolved in the water. They're all different ways of measuring and analyzing. In your saltwater tank, total dissolved solids aren't going to be very meaningful to you. You're more concerned with TDS, total dissolved solids, in your source water that you're going to use to mix your salt water. In a sense, it means the same thing as salinity, but context is important here. So when we talk about TDS, we're talking about the stuff that's dissolved in your tap water. You can measure it with a conductivity meter. And if you have high TDS, you want to get that stuff out before starting mixing your seawater. When we talk about hardness, we're talking specifically about metal ions in the water. And the two most important ones we'll run into are calcium and magnesium. So again, these are things you want to remove from your fresh water before starting making your saltwater mix. And then when you get into advanced reef keeping and you have animals that are pulling these things out, now you want to be concerned with putting them back in. We're not going to cover advanced reef chemistry today, though. We refer to water's hardness in terms of being hard or being soft. We measure it in degrees of hardness or micromoles per liter or ppm. We can remove these dissolved ions, compounds from water in a reverse osmosis unit. This shows a schematic of an RO unit that's made for making fresh water out of salt water, but we use it for purifying our fresh water before starting making our salt water at home. The one I use is this one from Bulk Reef Supply. There's a lot of different RO units on the market. A lot of them are just the same components put together by different companies. I really like the ones that are put together by BRS, though, because they're really put together with aquarists in mind. They consist of a membrane that pushes your solution across the membrane and holds ions back and lets the water go through. And then this one comes with a resin chamber at the end that removes any solids that don't get taken out by the RO membrane. This unit is under $200 and it's very effective. We break down the components of seawater into the major, minor, and trace constituents. I don't really have time to go over them right now, but basically these top 6 make up most of the salinity. We measure those in parts per thousand. And although salinity can vary around the world in different parts of the ocean, the proportions of those top 6 in natural seawater tend to stay the same. So technically, you could measure salinity by doing a chemical test on any one of those top 6 and then calculating the total salinity, which would be unnecessarily complicated. This just shows the basic components of seawater in a pie chart. Processes that put in and take out these dissolved components from seawater have been going on for billions of years on the planet and include a lot of different physical and chemical and biological processes. But we have good evidence to suggest that the basic makeup of our water chemistry in the oceans has been very stable for a very long time. We express salinity in units of, well, technically they say it's a unitless number. None of what we use to measure salinity is really directly measuring salinity. The only way to directly measure salinity really is to take a sample of water and weigh it and evaporate off all of the water and then weigh what's left. Also unnecessarily complicated. We have a bunch of tools that are pretty good at measuring indirectly the salinity, and we express it in parts per thousand or grams per liter, or what we call practical salinity units. Fresh water, of course, is around 0. Seawater averages somewhere in the range of 35 parts per thousand. One of the most common tools we use as aquarists is the hydrometer, which is not, again, directly measuring salinity. It's measuring the density or specific gravity, which is the relative density. You're measuring the relative density between the floating device that you're putting in the water, whether it's the arm of this one on the left or the floating glass thing on the right. And you're measuring the difference between that thing and water in terms of their density. When you're talking about salinity, make sure you use the right units, though. I have a lot of people tell me, well, the salinity was 1.022 or 1.025. That's not salinity. That's a density measurement. Some people further abbreviate that 1.025 and just say it was 25. And now I don't know. Do you mean it was 25 parts per thousand, or are you abbreviating 1.025? So try to keep your units straight and sound smart. Another way we measure it, again indirectly, is with a tool called the Refractometer that measures how much light bends when it goes from the atmosphere into a liquid sample. So again, even though it's a very accurate measure, it's not directly measuring salinity. It's measuring really the relative density between the atmosphere that the light's moving through and the water. The speed of light changes a little bit. It bends when it moves from the air into your water sample. And that bending is going to vary based on what that density difference is between the atmosphere and the water. And the more stuff that you have dissolved in your water sample, the more bending is going to occur, and it shows up as where this blue-white line appears, and usually has a reading for salinity on the right and specific gravity or density on the left. Now, another way we measure salinity is using the conductivity of a water sample. Pure water is not conductive. Electricity doesn't flow through it. The more dissolved ions you have in there, the more easily electrons moving through can complete a circuit. So a conductivity meter is measuring the resistance or conductivity of your sample, and that's giving you a good, very accurate reading of salinity also. It's just showing variations in salinity. Notice where you have circulation patterns keeping ocean water away from the coasts, you can end up with salinity that's a bit higher. So some variation in salinity across the world's oceans, which is why most of what we keep can tolerate some changes in salinity, even though not very big changes. Another interesting point about global salinity is that even though it tends to increase as you move toward the tropics, there's a dip in salinity around the equator from the same band of increased rainfall that gives us our tropical rainforests centered around the equator. There's a lot of great salt products on the market. My favorite these days is ESV salt. It adds a separate step in terms of having to mix components separately. But after talking to Bob Stark and realizing he's one of the smartest guys I know in terms of water chemistry, I really trust him to make a good product. The reason it makes good sense to have the minor and trace components separately is that those are the really expensive parts of putting together salt. And so if you buy laboratory grade, really super pure minor and trace components for your salt, they can be 10 times the price as less pure components. The other big thing you're paying for in salt is the actual sodium chloride and magnesium sulfate, which is very heavy to ship around. And you can buy you can buy your sodium chloride and Epsom salts locally, and they make this in massive amounts, very pure because it's made for human use, and save a lot of money and just buy these minor and trace components, the Part A and Part B. And what Bob does with those components is he buys not terribly expensive trace components and then dissolves them and runs them through a filter to remove all those impurities. So when you mix this stuff up, it comes out. I'm not just trying to plug ESV here. It really does mix very clean, and I've used it for a long time with great results. One of the things that makes it especially easy to use is an inexpensive electronic balance to measure out all the components by weight instead of by volume. The next thing we'll touch on is pH. Most of us have a vague idea of what pH is, but I want to give you a little bit more of a background on it. We have this idea. pH has to do with how acidic or how basic water is. Sometimes they use the term in textbook alkaline instead of basic, which there's some overlap, but it doesn't mean exactly the same thing. Alkaline or alkalinity is not a synonym for basicity, and the word gets a little bit abused. So we have this vague idea of what pH is. Before you can understand it, though, you have to go back to the water molecule. We said it's a really, really good solvent. So good, in fact, that water tends to dissolve within itself. It ionizes. Water molecules can sort of tug each other apart, and you end up with a positive and negative ion, what we call the hydroxide ion and the hydrogen ion. This is a negative ion and a positive ion. This one has one extra electron. The hydrogen ion is just a proton. It can also go the other way. Whenever a hydrogen and hydroxide ion get together, they can get together and reform the water molecule. So you have this reaction taking place in both directions in any sample of water. Also, sometimes that, or very often, that hydrogen ion will encounter a water molecule and form what we call the hydronium ion. In talking about pH, we don't really distinguish between this guy, the hydronium ion, and the hydrogen ion. They're effectively the same. They're positive ion made up from water. So we use the term pH to characterize the acidic or basic nature. What it really is a measure of the hydrogen ion concentration, and it's inversely proportional to what we would call the pOH, or the hydroxide ion concentration. But you don't need to measure both. By convention, we just measure the hydrogen ion concentration because they're completely inversely proportional. If you know one, you know the other. So we measure the hydrogen ion. In general, acids add hydrogen ions to a solution. Bases add hydroxide ions to a solution. That's one way to look at it. These two, again, are inversely proportional. So what does the pH exactly mean? If you have something with a pH of 6, that means it has 1 times 10 to the negative 6th watt. That's the concentration of the hydrogen ion, moles per liter. A mole is a really big number that we use in chemistry to measure concentrations of atoms and molecules. It's a word for a number, like the way a dozen is a word for 12. A mole is a word that describes this number, 6.022 times 10 to the, 6.023 times 10 to the negative 22nd, whatever, some really big number. And so we use scientific notation, and we've come up with the pH scale. So if it has 1 times 10 to the negative 6th moles per liter of hydrogen ions, we say it has a pH of 6. 1 times 10 to the negative 7th, that's a pH of 7, and so on. We invented the pH scale to try and make it easier to talk about these numbers. So once in a while, I'll have a student ask me, what is it? So pH, it's the negative log of the hydrogen ion concentration. Why don't we just say the concentration? Why do we have to invent this whole complicated scale with this complicated definition and negative logarithms and make our life miserable? And the reason is because it's a mouthful to say that something has 1 times 10 to the negative 8th hydrogen ions per moles per liter of hydrogen ions, or 0.000000001 moles per liter, or 1/100 millionth of a mole per liter of hydrogen ions. It brings the numbers down to earth. So that pH scale, which I should have put again here, goes from 0 to 14. Those aren't the absolute extremes, but most of the things we deal with fall between pH 0 and pH 14, and things with a pH of 7 are considered neutral. In other words, the same number of hydrogen ions as hydroxide ions. We're not going to talk about all the possible dissolved gases, but CO2 is an important one, partly because it's so soluble in water. Did you ever wonder why our soda is carbonated and not oxygenated? We use carbon dioxide in soda because it's very, very soluble in water, 30 times more than oxygen, 50 times more than nitrogen. We also know that CO2 affects pH. And it's interesting because when you look at CO2, it doesn't have any hydrogens or hydroxides to contribute, but it appears to be like an acid, because when you add CO2 to water, the pH goes down. The hydrogen ion concentration goes up. The reason for that is because when CO2 combines with water, it forms this molecule called carbonic acid. It's an acid because it does have hydrogens to donate. It loses one hydrogen and becomes the bicarbonate ion, which loses another one and becomes the carbonate ion. So as those hydrogens are shed, the pH is going down. But another thing about any sample of water that has all of these molecules and ions in it is that it creates something called a buffer. When all of these are present, you can add some acid or some base to the solution, and it will resist changes in pH, because if you add more hydrogens, then it shifts the reaction back this way. Carbonate goes back to bicarbonate, bicarbonate goes back to carbonic acid goes back and releases CO2 into the water, and same if you add a base. So it gives some resistance to changes in pH, which brings up the next term, alkalinity. Alkalinity really is a measure of a solution's resistance to changes in pH. And usually alkalinity tests are done by adding, titrating, meaning adding a little bit of acid at a time to a solution and looking for a color change with a reagent that is set to change color at a specific endpoint pH. Most of alkalinity is due to the presence of carbonate and bicarbonate ions in a solution. And we can measure it in milligrams per liter, which is the same as parts per million. Typical seawater ranges around 115 to 120 milligrams per liter in total alkalinity. We mentioned the relationship between CO2 and pH. So in any body of water where there's light coming on during the day, whether it's a pond or the ocean or your fish tank with lights on a timer, the pH is going to vary between day and night because as photosynthesis takes place, CO2 is removed from the water, and that causes the pH to go up because there's less carbonic acid. It shifts that reaction we talked about. As photosynthesis ceases at night and respiration continues, there's an increase in CO2, so more carbonic acid, the pH goes down. So we know that pH swings, in fact, any kinds of big changes in water chemistry are stressful for our animals that are adapted to very, very stable conditions. So with higher alkalinity, you get less of a pH fluctuation from anything, including that day-night difference from photosynthesis. So it helps to stabilize your pH if you have higher alkalinity. The next thing I want to mention, the next topic, nitrogen, the dreaded N word. Nitrogen, like water, remember that thing where God put all that water on the planet and made virtually all of it undrinkable? Well, he kind of did the same thing with nitrogen. Every living cell on the planet needs nitrogen. It's a very important component in so many parts of our cells, especially in proteins. And that nitrogen gets into living systems from plants who take it from the soil or from algae cells in the ocean. But most of that nitrogen, so most of our atmosphere is nitrogen. Nearly 80% of our atmosphere is nitrogen, and that's completely unusable by plants and by algae. There's virtually no usable nitrogen naturally occurring, but it's there, thankfully, because pre-life on this planet, there was some ammonia, toxic ammonia, in our atmosphere. Probably was the nitrogen source for the first amino acids that ended up being assimilated into the first cells. Some of the bacteria that have been around for billions of years making use of that nitrogen are still around today. So we have this thing that we talk about, the nitrogen cycle, in nature, in soil, in our fish tanks. Nitrogen is excreted by a lot of aquatic organisms as ammonia, and ammonia is very toxic to our aquatic life. One type of bacteria breaks it down into nitrites, a little less toxic. Another type breaks it down into nitrates, much less toxic. And some other types are capable of using nitrates, usually at a much slower rate. So the nitrogen cycle, primarily in our tanks, we're dealing with these three molecules or ions, as the case may be. When we talk about cycling our tanks, though, we really mean we're conditioning our tanks, right? The tank isn't going through a cycle. It's not a cyclic process. When we say we're cycling the tank, what we mean is we're establishing all those bacteria that will eventually take part in the nitrogen cycle. Another thing to point out here is that ammonia, the molecule, is very toxic. Ammonium, the ion, is much less toxic. Notice the difference? This one has one more hydrogen than this one. That means, and you've probably heard this at some point, that at lower pH, meaning more acidic water, ammonia becomes less toxic. What happens is ammonia converts to the ammonium ion, which is less toxic. This becomes a big issue when you're shipping fish. pH goes down in the bag as respiration's taking place. There's more hydrogen ions. They combine with the ammonia molecules, form ammonium ions. Now there's ammonia building up, or ammonium building up in the bag, not so toxic. You open up your bag, you pour in a little water from your tank to start the acclimation process, and all of a sudden that ammonium reverts back to ammonia, and your fish are suddenly stressing and dying from ammonia toxicity. So something to take into account in acclimating fish. The process, this is an abbreviated version of the chemical pathway that these bacteria undertake to convert ammonia to nitrate. Notice that hydrogen ions are released, so this process is lowering pH, another thing to think about. These other bacteria that convert nitrite to nitrate, this is that pathway. The reason we have biomedia is to give a place for a lot of that stuff to live. These bacteria live in biofilms on every surface of our tanks, the plumbing and the walls and the gravel and the live rock. Biofilters, which, like with these bioblocks, which probably most of us don't even use anymore, are basically just a haven for those bacteria to live. When you're cycling your tank, if you were to track the levels of those three compounds, ammonia, nitrite, and nitrate, the curves would look something like this. Your ammonia would peak first and then come down. Your nitrate would peak then, and then very slowly your nitrate would be climbing. So, as we mentioned, nitrate is much, much less toxic than ammonia and nitrite. Probably we all know this, I understand, but it takes a lot more nitrite to be toxic to fish. This is from my aquaculture course, looking at the toxicity of ammonia to some species that probably none of us here care about, but it's to illustrate a point. This is called the LC50 test. What concentration you have to have of ammonia to kill 50% of the animals in a sample. Notice there's a pretty big variation. Shrimp can withstand much higher ammonia than salmon and trout. But the real thing I want to point out is that the nitrate toxicity, look at how much higher the concentration needs to be of nitrates to kill 50% of the animals. It's very, very high. So what that means is you can have a lot more nitrate than ammonia or nitrites without killing your fish. But we never let our fish or our animals die of nitrate toxicity. You're never going to let your nitrates get to these levels. We want to keep our nitrate levels down for other reasons, because long-term exposure of just 20 or 30 or 50 parts per million can cause chronic health problems for your animals. Corals, of course, are much less tolerant of those kinds of levels. And probably more basically for most of us, that nitrate acts as a fertilizer. It's an important nutrient. It's the nitrogen source for the algae that you're always fighting in your system. So we want to keep nitrate levels very, very low to help fight that war against things like algae and cyanobacteria. Phosphorus, which plagues us as phosphate in our systems, is another product of organic decomposition. If anyone ever tells you that they have fish food available, this happened a couple years ago, fish food that has no phosphates or is low in phosphates, they're either lying or they're selling you something that isn't food, because phosphate is extremely abundant in every living cell, in every organism on the planet. It makes up a big part of the cell membrane of every living cell. It's an important component in all of the nucleotides that make up nucleic acids, DNA, and RNA, and ATP. So it's very, very abundant. And as anything breaks down, any living material breaks down, phosphates are going to get put into your water. So all of these pesky compounds that we're trying to keep at bay in our tanks, we can test them with a variety of different tools. The spectrophotometer measures the concentrations by you put a water sample in and it shines a light through, and it measures how much of that light gets absorbed at what specific wavelengths, and it can tell you concentrations of things. And colorimeter does kind of the same thing. using reagents that create a little bit of a color change, and basically the light that's shining through, it's basically reading the color for you that you would normally do in something like a reagent-based test kit. There's electronic meters and probes that are useful for some things like salinity and TDS and for pH, not necessarily for all of the parameters, but these are some of the different kinds of testing tools. Me, as a very simple-minded and lazy aquarist, rely on something pretty simple. I use the API test, and I obviously don't test for everything, but simply because this is the test kit that's available in the pet store that's close to my house, so that's the one I use. In the end, for the average hobbyist, I mean, if you're not an advanced reef hobbyist, you have a fowler system or any kind of fish-only tank or a very simple reef tank, a lot of your effort centers around controlling just nitrate and phosphate. All that other stuff, if you're sensible and do your water changes and aren't careless with stocking and feeding, should really take care of itself. We focus our efforts on nitrate and phosphate. How do we keep it down? Chemical filtration like activated carbon and granulated ferric oxide. I like to have a little double chamber, one with activated carbon and one with phosphan, and it does a great job keeping these things at bay. Algae reactors, like if you can afford the top-of-the-line Pax Bellum chaetomorpha reactor, this can do such a good job at removing these things that you sometimes have to add nitrate to your system just to keep the chaetomorpha growing, because it pulls out so much it starves itself. Or you can just keep a sump with a good light and grow some algae in there. Denitrification, another process that we don't really have time to get into, but some people will use a denitrifying filter where you create a chamber with no oxygen and basically create a culture chamber for a species of bacteria that will break down nitrates and end up releasing nitrogen gas. I think going too far and trying to just control nitrates, though, sometimes is, well, I think that nitrates sometimes can serve as a good indicator that it's just time for a water change. We tend to forget that even though we're testing for 3 or 4 or 5 things in our tanks, there are thousands of different chemical interactions going on, and things are going farther and farther askew in between water changes. Some good prevention of nitrates and phosphates is just being sensible with how much stuff you put in your tank in terms of animals and also in terms of food. Mechanical filtration does a great job if you maintain those mechanical filters properly. So a filter sock or pad is great at removing organic stuff before it has a chance to break down and give rise to things like phosphates and nitrates, but only if you clean those things regularly. If you're letting the stuff sit there and rot inside your filter sock and letting it go for weeks without changing and cleaning it, then you haven't gained anything at all. Protein skimmers also, if they're well maintained and kept clean, protein skimmers act by creating a very high surface area of air-water interface, and that little charge difference where the water molecules are at the surface has an affinity for lots of polar regions of organic molecules and foams them out. But again, they only keep working well if you keep them cleaned and well maintained. A really well-designed sump where you can separate some of this stuff out, whether it's through good placement of your mechanical filters or settling chambers, things like that. Good flow is really important too. If you have dead areas, even, we tend to forget about flow when we're not keeping things like fancy corals, but flow is very important in any tank, because any dead spot in the tank, you're going to get detritus falling in a place out of sight somewhere, and that's going to decompose and release these organics into the water. Strategic siphoning, finding those areas and siphoning that stuff out. But most importantly, I can't emphasize this enough, just do your darn water changes. Sometimes we go so far trying to use all of this complicated stuff to keep our nitrates down that we forget that a simple water change might be cheaper and easier. And I want to leave you with this thought. It's very tempting. We all, I think, go into setting up a tank to think about our tank as a little slice of the ocean. But it's not. It's not a slice of, if your 100-gallon tank was really just a slice of ocean water, then it wouldn't look anything like what your tank looks like. The average 100 gallons of ocean water, if you wanted to keep a tank that was representative of the average 100 gallons of ocean water, it would have a couple of 100 billion viruses and a couple of billion bacterial cells and a few million algae cells and a few 100,000 zooplankters, and it would have no fish, because the average 100 gallons of ocean water doesn't have any fish. We look at a thing like sea foam at the beach and say, oh, it's nature's protein skimmer, removing all that stuff, helping keep the balance. But in reality, what keeps water in the ocean so stable and of such high quality is the dilution factor. Most of the ocean doesn't really have anything in it. We keep our tanks at very unnaturally high densities that are nothing like any sample of the ocean. So keep that in mind. You're not maintaining something that mimics nature. Your tank is a very artificial ecosystem and is nothing like what's happening in the ocean. So I hope that you took something away from my introductory chemistry talk. And I'd like to say, first of all, thank you to all of the people and companies that have helped me out and sponsored me over these last however many years. Thank you especially to my wife of now 10 years, who minutes before was frantically going through my terribly aligned slides and helping to make them look a little prettier, as always. And thanks for having me back to MACNA. I can't wait to get out on the floor and talk to all of you.